Now the next set of slides deal with characteristics of the hypothesis test. And so let's take a look at these. Recall the following characteristics of a test. Power is the probability of rejecting the null hypothesis. And in particular, it's the conditional probability of rejecting the null hypothesis when the null hypothesis is false and should be rejected. Beta is the probability of committing a type 2 error. Now remember that a type 2 error is failing to reject a false null hypothesis. In other words, if the null hypothesis is false, but we fail to detect that, we accept the null hypothesis as true, then that's a type 2 error. And beta, remember, is our notation for the probability of committing a type 2 error. Now, it turns out that power and beta are related through this relationship right here. So power is equal to 1 minus beta, or equivalently, beta is equal to 1 minus power, or equivalently also, power plus beta will always be equal to 1. That's a very important relationship that you'll need to understand and remember. Now let's investigate these characteristics in more detail. Now let's first talk about the power function. Power is a function of the true value of mu. So power is not a single number. Power is a function, and it depends on the true value of the population mean. Now I will also say that it depends on other things like the sample size, the significance level being used, the level of variability in the population. And so really power is a function of all those things, but for now I'm going to suppress those other characteristics, those other parameters in the notation for power, and just emphasize the fact that power is a function of the mean of the population. Now, the probability of a type 2 error is also a function of mu. Do you see why that would be? Let me go back to the previous slide. We said that power is equal to 1 minus beta. And so if power is a function of mu, then beta must be a function of mu as well. In fact, beta is a function of all those things that I said that power is a function of as well. Mu, the sample size, the significance level being used, the level of variation or variability in the population. So beta is a function as well. And so we can represent this function beta, which is a function of mu, we can represent it in functional notation this way. So we have the power function. Oops, let me go back. We have the power function, and we have the beta function. Now we can graph each of these functions of mu. We can graph the power function, and we would do that. We would graph the power function versus mu. So mu would be on the horizontal axis, and the power associated with various values of mu would be on the vertical axis. We could also graph the beta function against mu to get a sense of the performance of the test. Now the graph of the beta function versus mu has a very specific name. It's called the operating characteristic curve. All right, so the graph of the power function versus mu would be just called the power function curve. The function of beta versus mu, that graph is called the operating characteristic curve. And these functions depend on the type of test that we're performing. They depend on, in particular, the alternative hypothesis. And so again, depending upon the hypotheses we're testing, whether a two-tailed test, so test A, or test B, the left-tailed test, or test C, the right-tailed test. Now these are the three types of tests that we can perform. Now, before we look at formulas for the power function, formula for the beta function, let me ask you a question. For each of these tests above, each of the three types of tests that we can perform involving a population mean, what would the power function look like for an ideal test? For an ideal test. Now, what do we mean by an ideal test? Well, an ideal test would be a test that always draws the right conclusion. In other words, if the null hypothesis is true, then it never rejects that null hypothesis. And if the null hypothesis is false, then it always rejects the null hypothesis. So stated in terms of probabilities, the ideal test, if the null hypothesis is true, then there would be a 0 probability of rejecting the null hypothesis in that case. But for any situation where the null hypothesis is not true, the ideal test would have a probability of 1 of rejecting. And so with that in mind, what would the power function for an ideal test of a two-tailed test look like? What would the power function for an ideal left-tailed test look like? And what would the power function for an ideal right-tailed test look like? This is what the power function for an ideal two-sided test would look like. So again, the two-sided test is the null saying that the mean of the population mu is equal to some value mu naught, which I'm representing by this point on the number line, against the alternative that says that mu is not equal to that value mu naught. So again, this is a graph of the ideal power, or the power function of an ideal test. And so on the horizontal axis, this is where mu lives. On the vertical axis, we've got the value of the power function. Now again, if it's an ideal test, then if the null hypothesis is true, the probability of rejecting will be 0. On the other hand, for any value of mu where the alternative is true, in other words, for any value of mu not equal to mu naught, then the probability of rejecting the null hypothesis would be 1. And so that is what we've got here. Now, I should have put a dot right here. So in your notes, if you're going to write this down, put a dot right there. All right. So if the null hypothesis is true, then this is at 0. Okay. And so the probability of rejecting would be 0. On the other hand, if mu is any other value besides mu naught, so if mu is over here, or if mu is over here somewhere, then the probability of rejecting would be 1. So this is what the power function for an ideal two-sided test looks like. For an ideal left-tailed test, right, so the null hypothesis would be that mu is greater than or equal to mu naught versus the alternative that says that mu is less than mu naught. The power function for an ideal test would look like this. So any value of mu, right, that is consistent with the null hypothesis, so any value of mu here or to the right, in that situation, the null hypothesis would be true, and so for an ideal test, there would be 0 probability of rejecting that null hypothesis. On the other hand, for any value of mu that satisfies the alternative, so any value of mu to the left of that point, the ideal test would always reject, and so the probability of rejecting would be 1. And then finally, the power function for an ideal right-tailed test. Right, so the null hypothesis says here that mu is less than or equal to mu naught versus the alternative that says that mu is greater than mu naught. And so an ideal test would never reject if for any value of mu that is less than or equal to mu naught. All right, so there would be a 0 probability of rejecting if mu were here or to the left. On the other hand, if mu were greater than mu naught, then the ideal test would always, 100% of the time, reject us. So the probability of rejecting for any value of mu out here would be 1. Okay, so those are the graphs of the power functions for ideal tests. Now we're going to be looking at the operating characteristic function for a hypothesis test about the population mean. So again, we've got our 3 hypotheses. Hypothesis A, which is the two-sided test, hypothesis B, which is the left-tailed test, and hypothesis C, which is the right-tailed test. So depending upon which hypothesis we're testing, that determines the appropriate formula for the beta function. So in the following formulas, Z is the standard normal random variable, and this notation here represents the probability, it's the beta function evaluated at mu, it's the probability of committing a type 2 error as a function of the true value of the mean mu. And so these formulas show us how to calculate the probability of a type 2 error for various values, or whatever value of mu that we might plug in. Now I would point out, you can see from these formulas that not only do these probabilities depend on mu, okay, mu shows up there and there, in this formula here, in the second one mu shows up there, and in the third formula for hypothesis C, okay, mu shows up there. So not only do these probabilities depend on mu, but they also depend on alpha, they depend on sigma, and they depend on n. So we could list those as arguments to this beta function as well, but I'm just suppressing that in the notation. But anyway, these formulas tell us how to calculate beta for a particular value of mu. Notice that each of these formulas involves calculating what these endpoints would be, and then using the standard normal table to look up the corresponding probabilities. On the next slide, we have formulas for the power function. And so again, z represents the standard normal random variable, and then pi of mu represents the power function for the test as a function of mu. And so the power function, or the formula for the power function, again depends on whether we're talking about a two-tailed test, a left-tailed test, or a right-tailed test. Notice also that to calculate these probabilities, what we have to do is calculate the values of these endpoints, which depend on alpha, mu, mu naught, sigma, and the sample size. And then we look up these probabilities from the standard normal table. Now, the next slide, the next several slides give the actual power functions and graphs of what they look like. And as we look at these, I want you to mentally compare these graphs to the graphs of the power functions of the ideal test that we just looked at. So here is a graph of 3 actual power curves based on 3 different sample sizes. So the blue curve corresponds to a power function for a sample size of 10. The red curve corresponds to a power function when the sample size is 30, and the green curve corresponds to the power function when the sample size is 50. Now, each of these 3 curves is a power function for a two-sided test of a population mean. So, in other words, where the null hypothesis says that mu is equal to some value, mu naught, against the alternative that says that mu is different than mu naught. So these curves are for two-sided tests. And the reason we have 3 curves again is because we're looking at 3 different sample sizes. Now, for each one of these tests, we're using a 0.05 level of significance. And I can tell that because at this point on the number line here, where this vertical line is going through the axis, and the axis is down here, right? The red line here is not the axis. The horizontal axis is right here. And this vertical line is going through the hypothesized value mu naught. Now notice that when mu is equal to mu naught, for each of these 3 scenarios corresponding to the 3 sample sizes, the power function is equal to 0.05. Okay, so if mu is equal to mu naught, then the null hypothesis is true, isn't it? And we don't want to reject. But there is a possibility of rejecting, and in this case that probability is 5%. So we're using a 5% significance level for each of these power curves. Now, if mu is not equal to that value right there, if it's over here somewhere or if it's over here somewhere, then the null hypothesis is not true and the alternative hypothesis is. And when that's the case, we do want to reject the null hypothesis. Now notice that when mu is close to mu naught, that there's not a lot of power associated with the test. The probability of rejecting is still pretty small. But as we get further and further away from mu, so for example, if we look at a value, further and further away from mu naught, if we look at a value of mu, say right here, then the probability of rejecting is going to be larger. And you can see here, if we were to draw a vertical line through that point on the number line, that the power for each of these 3 curves, or for each of these 3 tests, we can see that it depends on the sample size. So if mu was equal to this value right here on the number line, if we had a sample size of 10, the power would be approximately 0.38. If we had a sample size 30, then the power would be about 0.66. And if we had 50 observations, then the power would be, looks like over 90%. Okay? So we can see here that the power depends on the sample size, and the larger the sample size, the greater the power. The other thing we notice is as mu gets further and further away from mu naught, the power increases. And that should make sense. As the true value of mu gets further and further away from that hypothesized value of mu naught, then it's going to be easier for our test to see that the null hypothesis is in fact not true. Now the last thing I want to point out on this graph. Again, notice the trend as the sample size is getting larger and larger. For any point mu on the number line other than mu naught, as the sample size increases, the ordinate on that graph, all right, the y value, gets higher and higher. Now, imagine that we increase the sample size to 100, or to 1,000, to 10,000. Can you see that the power curve is going to look more and more like the power curve for the ideal test? Remember that ideal test had a point down here, and then that horizontal line up there. So you can see here that as the sample size increases, the test is going to look more and more and more like that ideal test. No test in actuality, no real world test is going to exactly equal that ideal test, but as you increase the sample size, it gets closer and closer to the ideal test. All right, this is the power curve for a left-tailed test. And again, we're looking at 3 sample sizes, a sample size of 10 for the blue curve, the red curve is a sample size of 30, and the green curve is a sample size of 50. And again, you'll note that, well, let me first point out that, let's see, this is for a left-tailed test, and so values of mu naught here or to the right, this is where the null hypothesis is true, and we don't want to reject. On the other hand, values of mu to the left of mu naught, so over here, this is where the alternative is true, and we would want to reject. And so notice that as mu gets further and further away from mu naught, the power of the test, the ability for the test to detect that the null hypothesis is not true, it increases. The other thing to note is that for a given value of mu in the alternative hypothesis space, as the sample size increases from 10 to 30 to 50, the power increases. And if you think about what happens for sample sizes even above 50, what's going to happen to this curve? It's going to be higher and higher and higher. It's going to look more and more like that ideal test for a left-tailed test. And then finally, here are the power curves for a right-tailed test. All right, so values of mu at mu naught or to the left is where the null hypothesis is true. Values of mu to the right of that point are where the alternative would be true. We can see that as mu gets further and further away from mu naught in the alternative hypothesis space, that the power goes up and up and up, and asymptotically approaches 1. And also you can see that for a given value of mu, as the sample size increases, the power increases. And if we were to continue to increase the sample size, then the power curve would approach more closely to the ideal right-tailed test. Now let's look at a few more examples. So let's again consider this right-tailed test, where the null hypothesis says that mu is less than or equal to 100, against the alternative which says that mu is greater than 100. And again, we'll assume that sigma, the population standard deviation, is 5 units. The test will be performed using a significance level of alpha equal to 0.05, and a sample size of 25 observations selected at random from this population. For each value of the population mean mu below, compute power of the test, compute beta, the probability of committing a type 2 error. So we're going to compute both power and beta for each of the values of mu here. So here again, I've written down the hypotheses. It's a right-tailed test. The null hypothesis is that mu is less than or equal to 100. The alternative is that mu is greater than 100. Again, I'm just noting out here to remind myself that I'm assuming that sigma is 5 and that I'm using a sample size of 25 observations. Then I'm going to write down the formula for my test statistic. And I'm not going to plug in a value for x bar. I'm writing out the generic formula here, plugging in the hypothesized value in the values of any known population parameters or sample sizes. And so zcalc, the formula for the test statistic, is x bar minus the hypothesized value of 100 over the standard error of x bar, sigma over the square root of the sample size, so 5 over the square root of 25. Again, that's 1, so this simplifies to x bar minus 100. And the rejection region, the rejection rule, is to reject the null hypothesis if zcalc is greater than the upper fifth percentage point of the standard normal distribution, which we know to be 1.645. All right. Now, how much power are we going to have if the true value of mu is 100.5? Now, let me go back to the previous slide. These are my hypotheses. Okay? If mu is equal to 100.5, which one of these two statements is true? Well, if mu is 100.5, the alternative is true, and we would want to reject. So the question is, what is the probability that we will get a hold of a sample that leads us to reject the null hypothesis at the 0.05 level of significance if mu is equal to 100.5? That probability is given by the power of the test. And so we find, once we go through the calculations, using the formulas in the notes, that if in fact mu is equal to 100.5, the power of the test is only 0.1251. In other words, there's only about a 12.51% chance that we're going to get a sample that leads us to reject the null hypothesis when mu is equal to 100.5. So when mu is very close to the hypothesized value, it's going to be very difficult for our test to detect that the null hypothesis is not true. That's reflected in this low power. Now, to calculate beta, we could use those formulas given in the notes, but we could also use the fact that power plus beta is equal to 1, and we can rewrite that so that beta is equal to 1 minus the power. So we've already calculated the power, 0.1251, and so beta, the beta function, which again is the probability of committing a type 2 error, when mu is equal to 100.5 is 1 minus 0.1251 or 0.8749. And so what that means is that if the true value of mu is in fact 100.5, then the probability of our committing a type 1 error, or I'm sorry, a type 2 error is really quite large, 87.49%. Next, let's look at the situation where mu is equal to 101. In this situation, the alternative hypothesis, which says that mu is greater than 100, is true, and so we would want to reject the null hypothesis. However, we're going to reject the null hypothesis if and only if we get a hold of a sample that leads us to that conclusion. And so the question is, what is the probability that we get a hold of a sample that leads us to reject the null hypothesis? The related question is, what is the probability that we fail to get a hold of a sample that leads us to reject the null hypothesis? Well, that first question is given by the power function evaluated at 101, and the second question is given by the beta function, the operating characteristic function, also evaluated at 101. And so evaluating the power function at 101, we plug 101 in for mu in that function, and we simplify that expression on the right-hand side of the inequality inside the parentheses. And so we see that the power function evaluated at 101 is equal to the probability that the standard normal random variable exceeds the value 0.645. And from the standard normal table, we can see that that is approximately equal to 0.2578. And so based on this, we can see that when mu is equal to 101, there's about a 26% chance, only about a 26% chance of getting a hold of a sample that is going to correctly lead us to the conclusion that the null hypothesis is false. The beta function evaluated at 101 is obtained by subtracting from 1 the value of the power function, and so 1 minus 0.2578, and that gives us 0.7422. And so we see that when mu is equal to 101, there's about a 74% chance that we're going to get hold of a sample that will not lead us to reject the null hypothesis. Finally, let's look at the power function and the beta function, both evaluated when mu is equal to 102. So the power function evaluated at mu equal to 102 is obtained by plugging 102 into the expression that we came up with a few slides back. And when we simplify that expression on the right-hand side of the inequalities inside the parentheses, we see that the power function evaluated at mu equal to 102 is equal to the probability that the standard normal random variable is greater than negative 0.355. And from the standard normal table, that is approximately equal to 0.6368. And so we can see that when mu is equal to 102, a little bit further into that alternative hypothesis space, the power has increased to about 64%. In other words, when mu is equal to 102, there's about a 64% chance that we're going to get a hold of a sample that is going to correctly lead us to reject that null hypothesis. The beta function, the operating characteristic function, evaluated at 102, is obtained by subtracting 0.6368 from 1. That gives us 0.3632. And so we see that when mu is equal to 102, the probability of failing to get a hold of a sample that leads us to reject the null hypothesis has dropped to about 36%. So this example shows how the power function and the beta function, the operating characteristic function, both depend upon the true value of the mean. And as the true value of the mean moves further and further into the alternative hypothesis space, the power function increases. That is, it becomes increasingly likely that we're going to get a hold of a sample that leads us to correctly reject the null hypothesis. On the other hand, the beta function decreases as we get further and further into the alternative hypothesis space, which means that the probability of committing a type 2 error decreases. Next, let's look at an example that demonstrates how the power function and the beta function depend on the sample size. So consider again this test we've been looking at, where the null hypothesis says that mu is less than or equal to 100, against the alternative hypothesis, which says that mu is greater than 100. Again, we are assuming that the population standard deviation sigma is equal to 5. And also, again, we're going to perform the test at a significance level of alpha equal to 0.05. In this example, we're going to let the sample size vary, and we're going to look at the impact of that changing sample size on the power function and the beta function. Now, suppose that the true value of the population mean mu is equal to 102.5. For each value of n below, compute both the power of a test as well as beta, the probability of committing a type 2 error. So let's look at this first scenario where the sample size is 25. How much power do we have if the sample size is 25? And we can see here that the power is going to be 0.8023. In other words, we're going to have about an 80.23% chance of rejecting the null hypothesis when mu is equal to 102.5 if we use a sample of size 25. And in this case, the probability of a type 2 error would be 0.1977. So about a 20% chance of committing a type 2 error. If we increase the sample size to 50, then the power is going to increase to about 97%, 0.9706. So if we use a sample size of 50, the probability that we get a hold of a sample that leads us to correctly reject the null hypothesis is 0.9706. There's about a 97% chance of that. And the probability of a type 2 error in that case would only be about 3%, 0.0294. And finally, if we increase the sample size to 75 observations, then we are virtually assured of getting a sample that's going to lead us to reject the null hypothesis. There's a very, very high probability that the test is going to be able to determine or detect the fact that the null hypothesis is not true when mu is equal to 102.5. And the probability of a type 2 error when n is equal to 75 is only 0.0036. All right, so in this scenario, for example, with a sample size of 25 or 75, remember that alpha, the significance level, is still 5%. Beta, the probability of a type 2 error, is 0.0036. And power is 0.9964. So we can see here in this example that while we have direct control over alpha, the significance level that we use for the test, and we don't have direct control over beta in terms of its actual value, because it doesn't have a single value. It's a function. It's a function of the true value of mu as well as these other parameters. We do see here that for whatever the true value of mu is, if we increase the sample size, we will be decreasing beta. All right, and so that's one of the reasons why we always want to get as large a sample as possible, so that we can reduce beta as much as possible. And then one more example before we stop this video. Consider this same hypothesis test, this right-tailed test, all right, where we're trying to show that mu is greater than 100. We're assuming that sigma is equal to 5. Suppose that it's required to perform the test at a significance level of 5%, and that we also want beta to be 0.05 if mu is equal to 102. So in other words, if the true value of mu is equal to 102, and if mu is 102, the alternative is true, right? And so we would want to reject the null hypothesis. So suppose that values of 102 or greater are significant or important to us in a given context, and so that's why we would choose this cutoff. Suppose that we want to determine the sample size necessary so that not only are we controlling alpha at 0.05, which is what we have direct control over, but we also want beta, which is the probability of a type 2 error, to be small as well. And in particular, we want it to be, in this case, 0.05. What sample size is necessary to satisfy these two requirements? So you see here, this is the kind of question that we can consider when we're designing our experiments, so that we can, based on assumptions about levels of variability in the population, and taking into consideration values of the parameter that are either clinically relevant or scientifically important, we can determine the appropriate sample size to use so that we're controlling not only the probability of a type 1 error, which is alpha, and which we control directly, but also the probability of a type 2 error, which is beta, and which we can only control indirectly. So how big of a sample size would we need in order to satisfy these two conditions? All right, so I've got my hypotheses listed up here, my significance level, and my assumed population standard deviation. This is the expression for the power. All right, so we know that power is a function of the true value of mu, the population standard deviation, the significance level that we're using, and the sample size. Now we know, or we've got a value for mu that we're specifying. We are assuming sigma is equal to 5, and we're choosing to use a significance level of 0.05 or 5%. The variable that we're leaving, the value that we're leaving variable is n. All right, and so this is what the expression for that power or probability looks like. So there's the unknown, right? The n shows up under that square root sign. So we want to find n, the sample size, such that beta, the beta function, is equal to 0.05. Now remember that beta is equal to 1 minus power. So if beta is equal to 0.05, power would be 0.95. And so we want to find the sample size n such that the power of the test is equal to 0.95. All right, now the power function, the probability for the power function, is the probability that the standard normal random variable z is greater than 1.645 minus 2/5 times the square root of the sample size. And we want to find n such that that probability is 0.95. Now, we know from the standard normal table that the probability that z is greater than negative 1.645 is 0.95. And so look at what we have. We have two probability statements. They both involve z, right? They both involve z being greater than some value. And both probabilities are equal to 0.95. And so that means that these two values, this value here and this value here, must be equal. All right, and so we come up with an equality that we can then solve for the sample size. All right, so if we do that, we see that n is equal to 67.65. And since we can't have a fractional sample size, we're going to use the next larger integer, which is 68. So if we select a sample of size 68, then we're going to be able to perform this test at such that the probability of a type 1 error is 0.05 and the probability of a type 2 error is only 0.05. So that is the way that we can control both types of inferential errors, by selecting the appropriate sample size. Now the next slide, this gives us a graphical representation of what we just did. We've got power curves for a right-tailed test. The significance level of the test is 0.05. All right. And we want the power, we want to find the sample size so that the power is 0.95. If the power is 0.95, then beta would be 0.05. And so we want to find the sample size such that the power curve at 102 is equal to 0.95. And we see here that as we increase the sample size, the power functions get higher and higher at any given point. So this point corresponds to mu being equal to 102. All right, and we can see here that the black power curve, which is a sample size of 70, okay, seems to, at least at the resolution given by this graph, intersect that horizontal line for a power of 0.95. And so based on this graph, we could choose a sample size of 70. But we saw, based on the analytical calculation on the previous several pages, that the required sample size is just a little bit less than that, 68. But this does show, graphically, the idea of what we were just doing. So this is, I'm going to stop here. This is the end of our discussion of power, beta, and things like that. And we'll continue on in the next lecture.